Hello. In this video, we're going to use a multi-layer perceptron, which is a type of neural network, to control a synthesizer that has 10 control parameters using just 2 control parameters that are in an XY control space. And we're going to do this using a strategy called regression. When we use regression, a neural network predicts output values that could go to anything from a set of input values that could come from anything. When we train the neural network, the first thing we have to do is collect a set of input and output example pairs. So, for example, here we have a set of input examples that each have 3 values, which corresponds to our 3 input circles here. And each of these input examples has a corresponding output example that has 2 values, just like our 2 output circles here. And each one of these input examples and output examples share a common identifier or ID to keep track of which inputs belong to which outputs. What we're going to do with all these examples is we're going to take them one by one and feed them into the neural network. We're going to send the input example into the input of the neural network, and at the same time we're going to tell the neural network, when I show you these input values, I would like for you to return these output values. And what this is doing is that each time the neural network receives an input example, it makes a guess on what it thinks the output values should be, and then checks against the output values I provided it to see how wrong it was. And then depending on how wrong it is, it'll correct itself a little bit so it can be more accurate next time. And after doing this training thousands and thousands of times, it starts to get pretty good at predicting the output values that I want it to based on the input values that I show it. So after this training is complete, we're then able to show it some values that it has maybe never seen before. And it's able to respond with an output that, although is not an example that I showed it, would sort of fit inside of the training data that I did train it on. So one way to think about this is if these blue dots are all of our data points and they sort of fit in this space in this sort of curved way, the neural network is able to learn this red curve that represents the general shape of my data. And that way, if I give it an input value that is not in the training examples that I showed it, it goes to this red curve and then is able to identify, if this were an input point, what output point would this correspond to so that it fits within my training data. Because I said the inputs could come from anything and the outputs could go to anything, we can start imagining that this could be used in all sorts of different ways. We could have a control interface be the input to the neural network, and then the output be controlling synthesis parameters on a patch. And this is actually what we're going to do today. Also, it could be from some sort of wearable or other input device. The input could have something to do with the audio analysis, like the pitch or loudness of a signal. And the output could be something else, like live visuals for a performance, perhaps. But really, that could be anything. And once you learn how to use a neural network for regression, the real creativity comes into what you're connecting it to and how you're using it musically. Here's the patch that we'll be starting from. You can see over here I have a 2-dimensional control space, an X and Y position on this 2D slider. And this is outputting by default values between 0 and 127. This first one is the X position, and the second one here is the Y position. And so I'm just joining those together into a list and then scaling that 0 to 127 range down to 0 to 1. So my input space will always be those 2 values between 0 and 1. And then over here on the right, I have this chaotic synthesizer patch, which you can download this whole patch in the description and take a look at this if you want. It's essentially a frequency modulation feedback synthesis that's kind of chaotic and difficult to control, so a good candidate for using with a neural network. And this 10 slider multi-slider is controlling the 10 control parameters of that synth. So if we listen to it, we can hear some of the varieties of sound that it makes. Notice that this multi-slider is outputting values between 0 and 1. So inside of this chaotic synthesizer, These values between 0 and 1 are being scaled appropriately to be in the range of loudness values or frequency values or whatever types of input for controlling the synthesizer. So we're going to train this neural network to receive this 2 values as input, the x and y position of this control space, and then it will predict 10 output values, namely the 10 control parameters for this synthesizer. Now, in order to train the neural network, we have to collect our input-output example pairs. And in order to do that, we're going to be saving these data points, these example pairs, inside of datasets. So I'll make 2 datasets down here by typing fluid.dataset. I'll name this first dataset XY data because it's where I'm going to put my XY positions. And I'll make another dataset here, and I'll name it synth params because it's where I will save my synthesis parameters. In order to add values to these datasets, I'm going to send them a message, add point. Add point takes 2 arguments. The first one is an identifier that will uniquely identify this data point within the dataset. I'm going to put a $1 there for now, and we will be replacing that with a unique identifier each time we add a data point. And the second argument is going to be the name of a buffer that the dataset should go look in to see what data is there and then add that data to the dataset. So I'll make a buffer in just a moment. I'll call it XYBuff. I'll better make that buffer. I'll call it XYBuff. And I'm going to give it the attribute @samps2. And this is going to specify that this buffer should have just 2 samples in it. Now, when we use buffers in Max, we're often putting audio files in them, which very commonly have 44,100 samples per second. And so we might have many thousands or tens or hundreds of thousands of samples per buffer in each of our buffers. In this case, because we're just going to have the 2 values, an X position and a Y position, we're going to specify that this buffer can just have 2 samples, and that's all it will ever have. So we'll give it the attribute @samps2. Now to get my X and Y position, which is coming out of this scale object here, into the buffer, I'm going to use an object called fluid.listToBuff, which does just what it sounds like. It will receive the list as input and then write those 2 values into the buffer. So I need to tell it with the attribute @destination which buffer to write into, which here will be XYBuff. And then I can just send it this list. So now if I pick a spot in 2D space here, maybe the X position will be rather high and the Y position will be somewhat low, and look in this buffer, I can see that sure enough, those are my X and Y points there. Okay, so now I have this data inside of this buffer and I can use that to add to my dataset XY data. I also need to get my output data, the synthesis parameters, into a buffer so I can add those values to the dataset synth params. So I'm going to make another message here, add point. I'm going to again put $1 for the identifier, which we will again pass in each time we want to add a data point. And then I'm going to put the name of a buffer here that I will use to add values to the dataset synth params. So I'll call it synth params buff. I better make that buffer, put it over here, called synth params buff. And I'm going to give this one the attribute @samps10 because I know that it will always only have the 10 values of the synthesis parameters in it. To get these values from this multi-slider into this buffer, I will again use the fluid.listToBuff, this time with @destination synth params buff. And now if I adjust the multi-slider and look in this buffer, I can see that sure enough, that looks like the correct set of values. Okay. So now that I have the data that I want to add to these datasets in these buffers, I can use this add point message to add them to the datasets. I need to pass each of these an identifier, and because when we train the neural network, we needed to know which inputs it should associate with which outputs to do the training, we're going to make sure that when we add these to the datasets, they will have the same identifier. So the neural network will know which output values it should predict from which input values based on that shared identifier. So I'm going to make a little collection of objects here that is going to create an identifier for us. I'll start with a bang. I will call this add points. And then I'm going to put a counter. And the counter is just going to give us a unique integer each time it receives a bang. And I'll just use that integer to make an identifier so that I know that each one of these identifiers are going to be unique because they will each contain a unique integer. So next I will put a combine object down here. And I'm going to put in the word point and a hyphen and then the letter S. And what combine will do is it will replace that S with the integer that I pass to it so that this identifier that I'm creating will be the word point, a hyphen, and then a number. Just a nice sort of identifier that will always be unique, but is also a little bit more explicit, a little more human readable, saying this is a data point, and where I'm identifying it with this integer. I'm also going to put in the attribute here at triggers 1, and what this will do is it will make this first inlet on the right as opposed to the 0th inlet on the left, because in this case we're start counting from 0. It will make this first inlet a hot inlet so that when it receives the integer, it will trigger an output. And we need to send the integer to the right inlet here because it is the first, where point dash is the 0th item here. S is the first item, so the integer should replace that first item. So if we just look at what's going on, we can see the output of this here. And every time I hit this bang, I'm getting a nice string that just says the word point, a hyphen, and then a new integer to identify it uniquely each time I hit the bang. So I'm going to use this identifier to pass to each of these add point messages. So now they will each use that identifier to add points to the respective data sets, pulling the data from whatever happens to be in those respective buffers. So now we can add some points to the data set. The way that I'm going to do that is I'm going to first find a sound that I like that I might want to include during my performance using this instrument. So this is a sound that I want to use. I'm going to leave this just as it is because I know that these synthesis parameters are in this buffer. Right, there they are. So they will be there when the add point message gets sent to the dataset. Now we need to make sure that the XY position is where I want it to be to associate with these synthesis parameters so that the XY position is in its buffer when I click the bang that will add the point to the XY dataset. So this sound, maybe I'll put it down here in the lower right-hand corner. It's totally up to me, but this might be, it's a little bit lower in frequency, it's a little bit grumbly, and so maybe that'll be a nice place for me to remember during my performance where it belongs. So now I'll click add points. I know that this is where I want it and this is where I want it, so let me click the bang. And then let's see if that stuff got added to the datasets. So I will send a print message here to both datasets. And if we look in the console, we can see that I have one dataset called XY data that has one row because I just added the 1 point. And it has 2 columns, which is good because it should have those 2 values, X and Y. And it has this 1 point in it that has the identifier point 13, and the X position is 0.9 and the Y position is 0.1. And then in the data set called synth params, I have again just the 1 row because I've only added the 1 point. That point also has the identifier point 13. That's good. So they have the same identifier. And it has 10 columns, which is going to be the 10 synthesis parameters that it read out of this buffer synth params buff. Okay, so let me add a few more points. I'll choose a new sound. Maybe I'll put this one down here. Got this where I want it, got this where I want it, and I'll click add points. And find another one. Ooh, that's a good one. Okay, I'll maybe put this one up here. So I got this where I want it, got this where I want it. That data is in the buffers, and I'll hit add points. And let me find one more. Okay, and I have the sound where I want it. I'll put this one up in the upper right hand corner. I got this data in the buffers, so then I can click add points. So now let's print that and see that. Here, let me clear it and print it again. We have in our data set called synth params, we have the 4 data points that each have 10 values. They range an identifier from 0.13 to 0.16. And in my dataset XY data, I also have 4 points ranging from 0.13 to 0.16, and they each have 2 values, the X and Y positions. Okay, so now I can use this data to train the neural network. This is the neural network that we'll be training. I'm not going to go over what these attributes do or why we might change them in this video. These are some settings that will work well for us today. There's a page on our site, learn.flucoma.org, that goes over all of these attributes and explains them, what they change, and why you might adjust them during training of a neural network. So in order to train this, I'm going to give it the message fit. Fit here is synonymous with train. It's like finding the line of best fit or fitting a curve to some data. And fit takes 2 arguments. The first one is going to be the data set that has the data that the neural network should use as inputs, which is going to be the data set that has our XY data in it, called XY data. So I'll give that the first argument. And the second argument is going to be the data set that the neural network should use for the output values, which is going to be our data set called synth params here. And remember that when the neural network does this training with these data points as the input and these data points as the output, it knows which outputs it's trying to predict from what input values, because the data in these 2 different data sets are paired with their shared identifier. So now, before I send this fit message into the neural network, I'm going to put a message down here because I'm going to catch out some information that it will provide for me. So now if I hit fit, it says fit. It has successfully completed the task that I asked it to perform, doing the fit. And it gives me this value, 0.55. So this value is called the loss or the error, and essentially it represents how wrong or how inaccurate the neural network still is at performing the task that we've asked it to learn. So in general, a lower value is better because it has less error. The predictions it is making are closer to, more accurate to, the output values that we've asked it to predict from our set of input values. There's no objective way that we can talk about this number, like if the fit is below 0.02 or something, it will be good for us. We can't really talk about it that way, but what we can do is watch how the number changes over multiple fittings. And we're going to hope that the number goes down. And if this number goes down, then it means the neural network is improving. It is learning from the data that we're showing it. And so we know that it is in fact getting better, and we can hope that once it gets better for a while, and it means it has gotten pretty good at making the output predictions that we're hoping it will make, at which point we then will start using it. So I'm going to hit fit again. It will do some more training. It's not going to reset the neural network or anything. It's just going to pick up from where it left off, and we'll see what happens. So it went down a little bit. That's great. It means the neural network has improved a little bit on this second round of training that we've asked it to do. I'll keep hitting it and see what happens. Oh, that was a big jump down, so that's good. Means it made a lot of progress there. And I'll just keep hitting it and see what happens. And it's going down pretty well. Now at some point, it will have progressed quite a bit lower from where it started, and it might start to flatten out, start to not be making as much progress on each fitting that we do. So it looks like we're sort of bottoming out at the 0.001 value here. So at this point, we have seen the value go down quite a bit and start to level out at a certain fit value, meaning that it has probably learned everything that it can learn from our data, and it's not improving that much. Even though we're doing more and more training, it's just not improving that much anymore. So it's probably learned everything it can learn. Now would be a good time to test the neural network and see if it is making the kind of output predictions that we're hoping it will make. So in order to do that, I'm going to send the neural network a message, predict point. And predict point is going to take two arguments. The first one is going to be the buffer that the neural network should look at to see what data is in there, what values are there to use as input to the neural network. Now, because our input is going to be the XY position of this dot here, and we're already writing those values into a buffer, we can just use that buffer called XY buff. The next argument is going to be a buffer that once the neural network makes a prediction, it will write its output values, the predicted values, into this buffer. So I'm going to make a new buffer called prediction that it will write the output prediction into. I better make that buffer. And I'm going to give it the attribute again at samps 10, because we know that our neural network is predicting synthesis values, and those values have, or those predictions have 10 values. So now, if I send in this message, it says predict point. It has successfully completed the task I asked it to do, which is make a prediction, and it's telling me that the buffer where it has written that prediction is called prediction. That's the name of the buffer here that it's printing out as well. So if I look in the buffer called prediction, I can see that sure enough, it has predicted some values and written them in here. So now we have the neural network trained, and it's making predictions from our input space to our output space. The last thing to do is to really connect some plumbing that will make it so that as I move around in this two-dimensional space, the neural network will make predictions based on wherever my dot is, and then use those predictions to control the synthesizer. So what I'll do here is I'll just notice that whenever fluid list to buff writes into a buffer, like right now, it outputs for me the word buffer and then the name of the buffer that it's written into. So that could be useful. I might want to use that in the future to pass that name, the name of that buffer somewhere else and do something with it. In this case, I'm just going to put a bang here, which essentially will mean that whenever it writes into a buffer, it will output a bang for me. And then I'm going to use that bang to trigger the message predict point. So now, whenever I move around in this two-dimensional space, this XY position will be written into the buffer, which will immediately cause a bang to send the message predict point to the neural network so it will make a prediction. So now if I move somewhere else in this two-dimensional space and check my buffer, I can see that there's some prediction values in there. If I move somewhere else and check buffer, there are some different values in there. So the neural network is now making predictions every time I move around in this space. Now what I need to do is I need to take this prediction and control the synthesizer with it. So down here, because whenever the neural network makes a prediction, it outputs the message predict point, I'm just going to select for predict point. And that will mean that each time it makes a prediction, I will get a bang. So now this bang, I'm going to use this to trigger an object to read the prediction out of this buffer and control the synthesizer with it. The object that we can use to do that is fluid.buff2list, which is the inverse of list to buff and does just what it sounds like. We'll take the values out of a buffer and pass them out as a list. I need to tell buff to list the attribute at source, which buffer it should read out of, which is going to be the buffer called prediction. And then I will send it a bang to tell it when to read out of the buffer. And the list that it reads out, I'm just going to put right into the multi-slider here, which will adjust the multi-slider and also be sent to the synthesizer. So now, if I move in this 2D space, I find a new set of synthesis parameters in this multi-slider. And again, they will also be controlling the synthesizer. Just to go over that data flow one more time. So every time I move in this two-dimensional space, these two values get written into the buffer XY buff using list to buff. Whenever list to buff writes into a buffer, it will trigger a bang here. and this bang is causing the message predict point to ask the neural network to make a prediction from the values in XYBuff, and then write the predicted values into the buffer called prediction. When the neural network is done doing that, it sends out a message that includes predict point here. So I'm going to select for predict point, which will give me a bang that I then can use to tell fluid.buffToList to read out of the buffer called prediction, where that prediction was just written into, so that I can have it as a list and control the synthesizer and the multislider here. So now we have the neural network trained. We have it making predictions in real time, so I can perform this synthesizer as an instrument. And we can hear that the places where I positioned those sounds initially in the corners are the sounds, or very close to the sounds, that I selected when I was doing the training or when I was creating the datasets. And you can see that the in-between spaces create in-between sounds. So I don't not only have the original sounds that I placed in this two-dimensional space, but I also have some relationship between them as I move between the spaces and across the space, so that the entire two-dimensional space is musically expressive for me. At this point, there's a few things that I could do if I like what I'm hearing. I could save this training of the neural network to disk by sending it the message write. And it will save the neural network state to disk as a JSON object, which I could then use, I could then load up in a performance and perform the synthesizer in this state that way. Also, if I'm not liking what I'm hearing, maybe I'm just not into the way that the sounds are working together inside of this space, what I could do is I could clear the neural network by sending it a clear message, and it would reset the neural network to a new state, and I would have to retrain it. But in that process of retraining, the neural network may end up in a different state that is going to have a slightly different relationship between the input space and the output space, and maybe that would be a more interesting instrument for me to explore. Another thing I could try to do is actually not train the neural network quite as much. So if I clear it here and then hit fit, we can see that I could maybe see what it sounds like here, or see what it sounds like after a few more trainings. And each one of these trainings where the fit value is different, the neural network is going to have a different association, a different mapping between the input space and the output space. And maybe one of those would be more musically interesting or musically expressive for me to play. And then the last thing I could do is, if I'm not liking the way that the input and output, the input space is being mapped to my output sounds, I could also just clear the neural network and also clear the data sets, make new points, starting all over, and maybe choosing different sounds or positioning the sounds more carefully in this two-dimensional space, or something else that might make the instrument more musical for me. And of course, you saw how quick it was to do this training and collect the data points, so it's something that you could iterate on quite quickly and find a set of inputs and outputs and a neural network training that is musically meaningful.